So, an example that maybe you're familiar with would be the idea that if you were, say, a crime scene investigator and you came in and you found this evidence, this is a plate of some kind, and it's been shattered into parts, would you be able to work out where the plate was before the shattering occurred? I'm really hoping you're saying yes, because you'd be able to look at the various sizes and positions of the pieces and you'd be able to say, well, these small pieces must have flown further than this large piece. If I look, I can find the centre of mass of this and find out where the plate must have been before the shattering occurred. And this, which I'm sure you'd all be able to do instinctively, even if you couldn't do it mathematically, is to do with centre of mass and momentum. Okay, so a more classic physics example that you probably will come across often and probably can get is the idea of ice skaters. And the idea that ice skaters, when they're standing touching each other, so they've got their hands pressed together, the centre of mass is between them somewhere, depending on their relative sizes. So the centre of mass is in the middle. Let's say without doing anything else, they push against each other. So they apply force on each other's hands. And we can see instinctively that they're going to fly backwards away from each other because they're on a relatively frictionless surface. So they're on ice, when they push their hands together, the net result is that they both fly backwards. And we know this is a Newton's third law consequence. We know that if A applies a force to B, then there will be a response force back on them. The net result being that the force on A is equal and opposite to the force on B. We don't know what's going to happen afterwards. You know, one of them could slip over. But we know that in the time when the force is applied, there will be a response force. Okay? Otherwise, there'll be some kind of unbalanced force acting. But in this particular case, the force that A experiences, the force that sends A flying backwards, is equal and opposite to the force that B experiences. We can extend that out into conservation of momentum, and we can say, well, the change in A's momentum must be equal and opposite to the change in B's momentum. And you'll notice that the centre of mass of the system stays the same. In this one, we've supposed that B is, well, my drawing has supposed that B is bigger, heavier, has more mass than A, and therefore B has not moved as far. A has moved further, but the centre of mass is still the same, it's stationary. The centre of mass has not moved. We're going to deal later with examples where the centre of mass is moving, but for now, let's work on this. Centre of mass stays still, the two objects fly away from it. If we look over here, we can see that the momentum of the centre of mass must equal the momentum of all the parts. And in our first example, in our ice skating example, that's really easy to see. The momentum of A flying backwards is equal and opposite to the momentum of B flying backwards. Therefore, the centre of mass doesn't move. However, in situations like we're going to see later where the centre of mass does move, we can say, well, the centre of mass must be the sum of all the masses times the velocity of the centre of mass. And you can see here how I'm leading up to situations where the centre of mass is moving. So we've got two separate systems, something's moving. And we end up with this nice formula here that the velocity of the centre of mass is the sum of all the momentums divided by the sum of all the masses. Now for this week, we're going to do some relatively simple stuff where objects are moving, but it's not too complicated. We're going to move on to situations where it's happening in two dimensions, where things are moving at angles to one another.